Hello, everyone. So let's talk about an algorithm for traversing the tree. By traversing the tree, we mean we want to go to each node and print the information or the value that is in their node. So basically, we want to visit every node of the tree and print it. So first algorithm that we are going to talk about is BFS. The elaboration of BFS is breadth first search. So breadth first search. Okay. So when you're talking actually breadth first search, we have to keep two things in mind. First is the breadth, and the second thing is a queue. We already know the queue data structure. Okay, first let's talk about the breadth. What is the breadth? So basically, what we understand is while traversing this tree or trying to visit every node in this tree, we want to go uh, towards the breadth first, not the depth. So instead of just going visiting this way in the depth first fashion, we want to go around the width or the breadth, right? So we want to visit this and then this and this and this, okay? So basically we want to visit towards the width first and then go to the depth. So breadth or width. Okay, so the result for this breadth first search is probably going to be 1, right? And then 2, 3, 4, and then 5, 6, 7, 8, okay, and so on. Okay, so to achieve this, one data structure that is going to be very helpful is queue. As we know, queue is a first in, first out data structure. So let's think in this way. When we are actually visiting this node 1, if we put 1 in the queue, and then once we are actually done visiting 1, if we check, okay, so okay, this is not a binary tree. Oh, but that's fine. This is not a binary tree, but it's still we are fine. Okay, so what we can do is we can check the children of 1, that is 2, 3, and 4. So what we can do is we can just put 2, 3, and 4 in the queue. So since 2, 3, and 4 are going into the queue, they will be also going out of the queue earlier than others, right? So that way we make sure that 2, 3, 4 are visited before these nodes are visited, right? Okay, so let's take a further look. Say this is a queue. This is our queue. You know, a queue is a container with both ends open, and things enter into the queue in this way and exit the queue from this way. Okay, so initially what we do is we put 1 into the queue. We put 1, okay? And then we start our algorithm, we take out 1. So we take out 1, and that means we have done visiting 1. But before taking out 1, what we do is we check the children of 1, and from left to right, we keep on adding them into the queue. So we take out 1, but we put 2, 3, and 4 into the queue. Okay. And so we will actually keep on doing this until our queue is empty. That means we have visited all the nodes. Okay, so the next item that we are going to take out is 2, right? So that means 2 is visited. Now we check the children of 2, which is 5 and 6, right? So we put 5 and 6 into the queue. We're done. Okay, next we take out 3. That means we take out 3. Now we check 3 doesn't have any children, so that means nothing goes into the queue. Nothing goes into the queue. Okay, so next, the queue is still not empty, so we keep on taking out. We take out 4. But once we are taking out 4, we check the children of 4, which is 7. We put it into the queue, and then we find 8. We put it into the queue. Okay, next we take out 5. So we take out 5 from the queue, and we put the children of 5, that is 9 and 10, into the queue. Okay, next we take out 6. 6 doesn't have any children, so nothing else goes into the queue. Okay, so 6 is done, taken out. Next we take out 7, and 7 has 2 children, which are 11 and 12, right? Okay, next we take out 8. 8 doesn't have any children, so we're done. We take out 9. 9 doesn't have any children, so nothing goes into the queue. We take out 10. Then we take out 11. None of these have any more children left, so nothing goes into the queue. And then we take out 12. So that's it. Okay, so using a queue, we are making sure that we visit the breadth or width first before we visit the depth, right? And the algorithm ends when the queue is empty. Okay, so we showed this algorithm for a tree. This was not a binary tree. Okay, but let's now take a look at let's now take a look at how the algorithm looks in Java if we apply it on a binary tree. Okay, so let's do this. Okay, so you see here that we have created a node class. We want to first create the tree, right? So every node has a value, integer value, and it has links to, since this is a binary tree, it has link to the left and right child. Those are also node types, right? So there will be one left node, one right node, and there's a constructor. We provide a value which initializes a node, and then initially the left and right are set to null. Okay. So next, what we do is inside this main function, we create the tree, and then we create 5 nodes, 1, 9 with these values, and then we assign B to the left of A, C to the left of C to the right of A, and then D to the left of B, and E to the right of D. Okay, and this is how the tree will look like. So this is the nodes, and these are their values, right? So if I want to do a BFS, this should look like this: 1, then 9 and 3, right? 1, 9, 3, then it will go to this level, 4, and then it will finally go to 10, right? So this is how the result of BFS should look like. Now let's take a look at the BFS algorithm. So it takes the root node of the tree, and then we define a queue. You see, we declare a queue, initialize a queue, and this is the way we initialize it in Java. And then we add the root node to the queue. Okay, we add the root node to the queue, and we check until the queue is empty, right? Once the queue is empty, then we are done. But until the queue is empty, we just take out one node out of the queue, print its value, that means we are visiting it, and then we check if the left of that popped node, right, is not null, then we add it to the queue, and then we check if the right child of the node is not null, we add it to the queue. Okay, that's it. Now here is one thing I actually missed. As you have seen that an empty tree is also a binary tree. So we have to check if root equals to null, then we just return. So we don't do anything, right? So we have to do this thing first, because if this is null, that means it's an empty tree. We cannot actually add this to the queue. Okay, so if I do this, and then if I try to run this, okay, and then in this main function, I have created a new instance of binary tree, and then I'm calling the BFS function. And for this tree, you see A was the root, right? Because A has no parent. So I pass A as the parameter, right? This is a root node. Okay, so let's remove this and try to run this. And you see my expected output was 193410, and that is actually achieved here. So the next question is, what is the complexity of this algorithm? As you can see, each node is enqueued once and then dequeued also once. Okay. So for the root node, only the root node is enqueued outside the while loop and dequeued here. All other nodes are enqueued either here in these two lines and again dequeued here. Okay, so one enqueue operation and one dequeue operation for each of the nodes. The complexity of the algorithm is order of n plus n. So this is for enqueue. This is for dequeue. This is order of n. Okay, so the BFS algorithm runs in order of n time on a tree.